Looks like it's time to start. Hello again, everybody. Um, Today we're going to continue with lecture 19 and then finish up with lecture 20. I just wanted to take a few minutes and talk about what's going to happen for the rest of the semester. We had the poll where I asked you all about your preference for the final exam. And it looks like about 2/3 of the people preferred to have the exam next week instead of in the final exam slot. So we're going to go ahead with that and have the final exam next Thursday evening. It'll be 7 to 10 p.m. And the format will be similar to the midterm exam. It'll be take home, do at home, open book style exam. So what we're going to do between now and then is today will be the last lecture with new content. And then next week, Tuesday lecture will be, I'll review topics for the exam and talk a little more about the exam. And then Thursday, we won't have a lecture in this slot, but we'll take the 7 to 10 p.m. time for doing the exam. Let's see what else. So homework, we'd like to get all the homework wrapped up and graded and back to you in time so you can use it to study. So we've accelerated things a bit. As you know, we posted a homework yesterday, which covers the material from this week. It's a shorter one, so you shouldn't have problems completing that by Monday. And then there's also, that was homework 12. Homework 11 is also due. That was from last week's material. That's going to be due on Monday also. So you have these two homeworks to do. We're going to try to get those graded in one day, so we'll get them back to you on Tuesday so you can use those to help prepare for the midterm or for the final. I think that's it. I'll have more information on Tuesday, and if you have any questions, you can ask me now, or you can post it in Piazza, whatever you want. Okay.
Hi, Professor.
Yes.
I have another class final exam at the same day.
Which class is that?
CS 162.
All right. Are they going to have an alternative slot?
Yeah, maybe.
I imagine that class is bigger, and they may have more conflicts than we do. So.
Okay, I will examine.
Check with them. If that doesn't work out for you, let us know. We could accommodate you, but I have a feeling they're going to have more conflicts there than we will. So I'm sure they're probably going to set up an alternative time slot. I think there's only a 1 hour overlap, right? Aren't they 5 to 8?
Yes.
Yeah. Okay. Well, check with them first, and then if we can't fix, we'll accommodate you if we have to. But it looks like that might be easier for now to go with them.
Okay.
So just let me know.
Okay. Thank you.
Anybody else? Okay. So on Tuesday, I started this lecture 19 on clock and power distribution, and we talked about clock skew and clock distribution, and this is mainly about designing ASICs. And where we left off was here in power distribution. So I'm going to continue with this now. There's a few slides here. And I'm trying not to introduce anything that's too deep or difficult now because we're getting close to the end. Okay, so this is all about distributing power. So the design constraint, or the kind of challenge for designing one of the challenges for designing ASICs these days is getting the power supply designed correctly. And that's because no power supply is ideal. It has some impedance. So here's kind of a model down at the bottom of the page. You'll see here's, you think of the power supply as a voltage source. It's providing VDD between ground and VDD. You connect that somehow into the chip, and that provides the VDD that we've been talking about all semester to drive the circuits. Unfortunately, this voltage source, by the time it makes it inside the chip, it's not very ideal, and that's for several reasons. There's a lot of current that flows when on the rising edge of the clock, let's say, a lot of changes happen inside. A lot of nodes flip, right? And those nodes continue to flip over a small amount of time as the logic signals kind of propagate through the combination of logic blocks. So that means there's a lot of current that has to be supplied to supply all the charge for changing all the nodes. Okay, so there's a large current on the power supply pins getting into the chip, and then once it's on the chip, on the wires on the chip. Because it's such a large current, any effective resistance is significant. And the same thing, because there's a large change in current, the inductance of the connections between the package and the chip, these could be bonding wires or solder bumps, and then the inductance of the wires on the chip also could be significant. So it's really two things we worry about. It's resistance and it's the inductance. Now remember, we can kind of understand the effect of the resistance by using Ohm's law, which says that a voltage is I times R. So if we have a certain amount of current flowing through this wire, let's say supplying some circuits on one part of the chip, you can multiply that amount of current that's flowing over here per unit time times the resistance here, and there will be a voltage drop. So even though we think we're putting 1 volt here, let's say, by the time instantaneously we'll see the voltage drop down a little bit because of the resistance of this wire. Right, so we get a voltage drop there. And the inductive effect is because, remember, inductance V equals L di dt. So there's going to be a voltage that gets developed across that inductor due to the fact that the current is flowing through it and that there's a change in the current. So if the chip is quiet and there's no currents flowing, then all of a sudden current starts flowing because we switched on some circuit, maybe because of the rising edge of the clock. There's going to be a kind of a burst of current that's going to flow through that inductor, and there'll be a voltage drop across that, right? So that's what happens. And so it's because of these high amount of currents that we have resistive effects and inductive effects that we need to worry about. And that's what we mean when we say that there's an increase in the impedance. Now, the typical target to keep everything working fine or well, we'd like to have so what we can do as designers, let me go back. As designers, we can do things to kind of help with minimizing the amount of resistance and the amount of inductance on the supply lines, right? So what we typically try to do is get the supply impedance to the point where there's only a 5 to 10% voltage variation from the nominal supply. So for instance, this would mean 100 millivolts for a 1 volt supply. Right? So that's a typical target. Now what's happened over time is, as we scaled down the geometry of integrated circuits, and if VDD is dropping as well, because that's part of what we do is scaling over the years is drop VDD. If the power is staying constant but VDD is dropping, what does that mean? Well, that means the current will go up, right? Because if the power is the same and VDD goes down, that means more current because power is V times I. So what this means is, in order to keep this 5 to 10%, we'd have to find ways over time to drop the impedance. Right? So it's become more and more of a design challenge, is to keep the impedance on the supply lines low. Here's an example from a chip. Let's say this is just made up, but let's say if we do the simple calculation here, we say let's say VDD is 1 volt and the power is 100 watts. That'd be a pretty powerful chip, but just say it is for argument. That would mean IDD, the current drawn, right, at this peak 100 watt operation of the chip would be on average 100 amps. It's a huge amount of current, right? So just looking at the resistance then, if you want to keep the voltage drop, IR voltage drop to 100 millivolts, that means we'd need to, that's 100 millivolts divided by that 100 amps, we'd need a 1 milliohm impedance on the supply lines. Right. So that's really small. Here's a maybe a more real world example. This is our IR drop example for the Intel Pentium 4. This is a chip that, it's a little old now, but it was kind of one of the most power hungry and high speed chips that was built. This was consumed about 104 watts at 1.275 volts. So that means the IDD is 81 amps. Right? So for a 10% IR drop, the total distribution resistance must be less than 1.6 milliohms. Right? If you look at the on-chip wires that are used for distributing power, they're about 20 milliohms per square. Right? That's the way we measure wire resistance on chip is ohms per square, because the thicknesses for a given layer of wires is constant everywhere. Right? So you can look for, and then each square of the wire looking down on top has a given resistance. In this case, for the thick wires that are used for distributing power and ground on the chip, it's about 20 milliohms per square. If we need 1.6 milliohms total, you can't meet this resistive requirement even with multiple complete layers dedicated to power. Okay. So what this has meant over the years is we've gotten away from the idea of supplying power and ground into the chip from the kind of the periphery of the chip, and kind of went to a flip chip packaging technology. Right? There's a picture here you can see. So here's the kind of substrate. This could be a printed circuit board or another silicon substrate. Here's our integrated circuit here, and there's solder bumps that are on the surface of the chip that are spread out over the whole surface of the chip, so that we can bring power from the substrate directly onto the chip to where it's needed. So we don't have to route power very far. Right? This creates a low resistance path from the substrate directly onto the chip to where power is needed. And a lot of these bumps then are just dedicated to supplying power. Right? If you look on the IC process, the IC itself, this is a cross section of a chip showing all the different metal layers. And these are the lower metal layers here, and these are the upper metal layers. So the metal layers, the ones down at the bottom that are close to the surface of the silicon, remember the transistors are all down here on the surface. These metal layers are used mainly for interconnect and then for connecting data signals. The upper layers are typically used for clocks and distributing VDD. You can see that they're, and VDD and ground. You can see these wires are thicker, so they provide a lower resistance path to supply all this current to where it's needed. Even with these upper layers of metal, though, it's still advantageous to use solder bumps, to bring the power directly onto the chip close to where it's needed. Right. So achieving this low impedance requires lots of resources. Typically 70% of the package pins are just these bumps. The pins onto the connections onto the chip are just for power. And as I've shown here, there's dedicated thick metal layers that are there just for providing power and distributing it locally on the chip. And here's just another, I showed you this picture earlier in the semester, but kind of just shows how the silicon die gets bump soldered down onto the substrate. There's another issue with supplying lots of power over resistive wires is sometimes if you put too much current, the wire kind of acts like a fuse and it will break, right? So there's a lifetime to wires. If a lot of current goes through this wire, over time, some of the metal atoms will get stripped away and the wire gets thinner and thinner. And then because it gets thinner and thinner, there's a higher current density through this narrower wire. As it gets wired, the thinner, the density of current goes up and up, which strips away more ions or more molecules, and eventually the whole thing just fuses. Everything gets stripped away and it's open circuit. So that can happen if the wires aren't wide enough or there's too much current going through a wire. So it's limited, as I say here, to about 1 milliamp per micron in width. This will provide a 5 to 7 year lifetime. And then just a typical way, if you look at a ASIC these days, there's the power network usually follows some predefined grid like this, or one layer of metal would form stripes this way, and another layer of metal will form stripes this way. And you can see here, alternate VDD. Here's VDD, here and here and here, and then here's ground here, here and here and here. So it creates this kind of power grid of VDD and ground using thick, wide metal. And then circuits will kind of tap off locally where they need, when they need power and ground. So I'm going to just skip. This just shows kind of the evolution of what, here's some chips that were built by Compact, and one generation of the chip used, they added this extra third layer of metal to help with providing power everywhere on the chip. And then in the next generation, and that used this kind of striped approach here. And the next generation added another layer of metal because the design got, VDD was dropped and the power was the same. So currents went up. So then they added another layer of metal and built this kind of grid. And in the third generation, they had to go to kind of dedicated solid planes. This is the lowest resistance way of distributing power and ground. So they had dedicated metal just for complete planes, and just punch holes in it from time to time to allow some signals to go through. Okay, so that was resistive drops. So that's one of the concerns. So that what I was just talking about mainly here was the resistance on the power lines, and that leads to a resistive voltage drop. Okay, the other part is the inductive part, and that's here. So the biggest concern, the major source of inductance is through the bonding pins. These are the connections to the chip package, right? In this diagram, it's these inductances here. The solder bumps I showed you have inductance. They're about 25 picohenries per bump. Bonding wires are actually much worse. In the old days, we connected chips to packages with bonding wires, and those bonding wires got cut off here, but they're about 1 nanohenry per millimeter of wire, and a bonding wire is usually a couple millimeters to connect a chip from the die to the package. And remember, as I said earlier, voltage across an inductor is equal to L, the inductance times the change in current through the inductor. So when the chip switches, it's switching all the time, but it's switching kind of synchronously with the clock edges. When these gates switch and they draw on current, there's some dIdt through these inductors. Now, the worst ones are the ones that are supplying current from the outside world, maybe the PCB or whatever it is, or the package to the chip. Okay, so here's an example. Let's say with a processor transient current is 50 amps, right, in 20 picoseconds from a 1 volt supply. So the question is, how many C4 bumps do we need to get the supply noise spike of less than 10%, so 100 millivolts? And then same question for wire bonds. We can use these numbers up here. So that's what's on this next page here. I do the calculation for you. So here's the processor transient current is 50 amps and 20 picoseconds on 1 volt supply. So we know V equals L dIdt. I just kind of rearrange that. So L is, we want to know what the inductance would be for a given voltage change, right? So here's the voltage here. I make it 0.1 volts. That's a 10%. I took the dIdt and made dTDI. So it's 20 picoseconds, 50 amps. If we multiply all this out, we get 0.04 picohenries. So that's the desired inductance. Right. Now we know that a C4 bump inductance is 25 picohenries. Right. So how many of these bumps do we need to get the inductance down to this point? You can see that one of them will have way too much inductance, so we have to use multiple of those. We put multiple connections in parallel. Inductors in parallel add, right? It's kind of like you divide up the current across all these inductors. Each one sees less dIdt. Right. So we can just do the division here, 25 divided by 0.04, 625. So we'd need 625 pins or solder bumps to supply the current to the chip in this case, if we want to keep the voltage spike due to the this dIdt down to 100 millivolts. And this is about right. If you look at large chips these days, they might have thousands of pins or 1,000 pins or more, and a good percentage of those, at least half, will be dedicated to VDD and ground. It gets much worse if we looked at the bonding wires. Let's say we had just a 1 nanohenry inductance in each bonding wire. We'd need more than 25,000 wires to bring the current in. So obviously for large, high power processors, we can't use bonding wires anymore. We used to in the old days when chips were much slower and lower power, but now everything has gone to bumps. And one of the reasons is for this inductance, because of the inductance limitations. Okay, so I think that's all I had in here. Oh, yeah, one more thing. So decoupling capacitors help with inductive and resistive effects. So a typical situation is you have the power supply here, maybe that connects somewhere onto the PCB. Then there's wiring, and then to the package, and then there's some bonding wire, or this could be probably a C4 bump between the package and the chip. So it's typical, as you know, if you've done any board design, to add decoupling capacitors. And what the decoupling capacitors do is we put some right next to the package on the board, and we actually design some right onto the chip. What these capacitors do is they kind of act like a local store of charge. Right? So on the chip, when the chip switches and it needs some current, instead of all the current having to come over the bonding wires or the C4 bumps, some of the charge comes from locally on this capacitor. Right? Same thing here when the outside the package, right? When the chip requires some current, instead of it all coming from the supply, some of it will first come from the decoupling capacitors. That means not so much current has to flow through those inductances, the inductance of the traces on the PCB. Right? So that helps minimize or mitigate the effect of this inductance here. Right? So the capacitors act, it's almost like a little battery, but they store the charge so that less has to come from across the wires. Right? And they kind of just stay charged up. And so what will happen is they'll slowly then charge up after the chip, while the chip is doing other stuff, I guess. The other way to look at this is these capacitors kind of form a smoothing filter on the supply voltage. If you look in the frequency domain, it kind of it filters out that kind of high frequency components. Right? So it kind of smooths out any of the glitches or the spikes on the voltage spikes on the supply. Okay, but it's the same thing. It really just acts like a local charge store. Okay, that's decoupling capacitors, and I think you've seen those if you look at motherboards, or you'll see these decoupling capacitors, and they're often mounted right under the die, either on the die substrate or on the PCB itself. Right? And they're sprinkled all over the PCB, right, to keep everything smooth and kind of provide local storage of charge. And same idea on the chip. Extra area that's not used for circuitry on the chip is often filled up with capacitors. So what this does is help mitigate any inductive effects and any of the resistive IR drops. And that's the end of this. Anybody want to ask anything about power clock? Okay, so in that case, I'm going to move on to this, talking about faults. So this is the last lecture, the last topic for this semester. I think it's a good one to know about, but again, not too much deep analysis here, just it's more informational. So I'm going to talk about faults in digital systems. So there's really three categories to this. There's design bugs, there's manufacturing defects, and there's runtime failures. Okay, so it's important to kind of keep these separate in your mind because we have different techniques for dealing with all of these. We would like our chips to be reliable, and we'd like them to be correct. Right? So design bugs should be obvious to you. These are bugs that you build into the design. They could be either bugs in the function, so the chip doesn't function the way you think it would. Maybe it makes some arithmetic mistake, for instance. Doesn't add numbers correctly, something like that. There might be timing bugs where it doesn't meet the timing spec, or there might be even a power draw bug where it draws more power than you want it to, right? So all these things are detected and should be detected and corrected at design time through testing and verification. And you've learned some techniques for this. We use simulation, we use static tools that can test for timing and perhaps power, maybe even function. Okay, so we have a bunch of things, mainly simulation based, to verify that our design is correct and there's no bugs there. We also have, there's the manufacturing defects. So once the chip, even if your design is correct and you have generated the layout correctly, there may be some manufacturing defects. And this could come up because you have some subtle violation of design rules. And so when the chip got fabricated, maybe two wires shorted out, right? Or maybe the design rule was correct, but it was marginal, that there was some weird thing that happened in the manufacturing. So things were not aligned correctly, and then you had something short out. There may have been some impurities in the chemicals that were used during processing, and that introduced some defects in the chip. And there could be just statistical variations in the width of wires and transistor widths and things which cause a defect. So this is detected through post-production testing and sorting. I'll show you some details of that in a minute, but we can test the manufactured chips to make sure that they're correct. And the other is that we could have some spare on-chip resources for repairing some of the bad parts of the chip. I'll show you that in a minute. And then, assuming it passed manufacturing tests, then there could be some runtime failures. And these are physical effects and environmental conditions. Maybe the chip gets too hot and it stops working. Could be some cosmic ray hits the chip, injects a bunch of charge, and that causes some failure temporarily. Right? So we're going to talk about all these in a little bit of detail. So the first thing is we'll talk about design bugs. So you're immersed in this now. If you're working in the lab, you're debugging your design, so you pretty much know what's involved in detecting design bugs and fixing them. But I wanted to give you one famous example. This was an Intel Pentium floating point divide design bug. You may have heard about this, maybe not. It was a few years ago now. In the mid-90s, there was a hardware bug in Intel Pentium processor in the floating point unit. The processor could return incorrect floating point results when dividing. And this was an example of what, if you divided these two numbers together, you get this result that's shown here versus this one down here. You can see in red, all those digits are in error. So it was approximately right, but not exactly the right. This was very upsetting to a lot of people who paid a lot of money for their Pentium processor. Even back then, these are $500 processors. Intel looked into it and they found out that they had made an error. There were some missing entries in the lookup table used by the floating point division circuitry. We didn't talk about division this semester, but often it starts with a table and then uses some table gives initial guesses and then it does some iteration to refine it further. But I guess they had a problem with their table. Why this wasn't detected, who knows? Maybe they didn't have it. The thing about testing designs, as you know, you can't test for every possible input always because it would take too long. So usually there's a testing technique where you test corner cases, you test for all zeros, all ones, you test randomly, and you do a bunch of random tests. And when you stop, when it kind of stabilizes, where you put more tests in and you get no more bugs, then you assume that you found all the bugs. But maybe that's what happened in this case. They just didn't have time to test it completely. In any case, Intel had to recall the defective processors. They had to pay or take back the old ones and give people new ones, or return people's money. So in the end, it cost them almost $500 million to deal with this error. So it kind of, the lesson here is you have to be really careful when you're shipping products that there's no bugs, because it could cost you more in the long run. They could have probably found this bug and detected it and fixed it during the design for a lot less than $500 million for sure. Right. So that's kind of the most famous case. Most designers are pretty careful these days when it comes to designing chips. It's one nice thing about using FPGAs. If you do ship a product with an FPGA in it, there's a chance you could fix it later because you could change the programming of the FPGA to rectify the bug after the fact. Okay, so dealing with manufacturing faults, what usually happens is designers of chips provide some test vectors. So when the chip gets manufactured, when they tape out the chip, they also generate some test vectors. There's some software that helps do that called automatic test pattern generation. These test patterns then are loaded into large testing machines, which are part of the manufacturing process. So after the wafers are fabricated, they're probed. So what you see here is a wafer probe machine, which would be part of one of these big testers. So these big testers hold the test patterns. They have these little probes, which come down onto the surface of the chip, because the chips are not cut away from the wafer yet. It would be too expensive to package all these die that are faulty, because there's going to be a good percentage of the die on the wafer that are not good. So rather than packaging them all, first we figure out which ones are good, and then the ones that aren't good gets marked. They get marked and get disposed of, and the good ones that are the ones that actually get put in the package. So this kind of manufacturing testing, it will package the, will test the parts before they get packaged. There may be some testing after packaging first, but this is the main test to use to figure out which ICs are good, and maybe even do some speed tests so they can be binned for a different speed grade. Right? There's also often some special test circuits that are built into the chip to help make it testable. For instance, memory blocks, caches, and big memory SRAM blocks on chip, which would be very expensive to test because it would take a long time on the testing machine. The testing machines these testers are expensive and usually pay per hour for using one. So you'd like to be able to test a chip as quickly as possible. So providing all those and providing tests from the outside world is slower than having the chip test itself. So more and more these days, there's kind of built-in test techniques. A very common one is inside memory structures, where you can build a little memory tester that will write and read locations in memories. It's a little finite state machine that cycles through all the addresses, writing some unique patterns and then reading those patterns back and making sure everything's okay. So it's easy enough to build that into a RAM block so it can test itself. The other technique is something called scan chains, where all the flip-flops on the chip, instead of being normal flip-flops, they act like normal flip-flops, but they also have a connection to other flip-flops so that they can form a long shift chain. So what this allows then is the testing of finite state machines and other blocks by just testing the combinational blocks separate from the flip-flop parts. So you can kind of break the You can kind of scan in a pattern, maybe run the chip for one cycle. That pattern will go through all the combinational blocks and then read out the pattern on the flip-flops and can see if all the combinational blocks were functioning correctly. So that's the scan chain technique. Okay, so manufacturing. So we can test to find manufacturing faults. We talked about this earlier in the semester. The faulty chips are discarded once they're tested, and the more chips we discard, this effectively raises the cost of a good die, right? And in fact, the reason why die cost goes roughly with the area, strong function of the area, is that as we make the area bigger, we have a larger chance of capturing a defect, and that's what that could kill the whole die. But sparing can help increase yield. So in the sparing technique, what we do is we have extra on-chip circuits that can be wired in after the chip is fabricated, and they can be used to replace the faulty sections after manufacturing. And this kind of comes up. This is used, for instance, for DRAMs and flash memory. Some FPGAs do this. Multi-core processors. It was done traditionally in magnetic disks. So the idea here is, I've shown it here. Let's say this is a DRAM chip, and there's a lot of DRAM cells here in the middle. Some of them would be dead because of defects in the manufacturing. Right? If we have some spare rows and columns, so here's some spare rows here at the bottom and spare columns here. Right? Those can be use a laser to fuse them in. They can be connected into the array to take the place of these bad rows and columns, which get deactivated. Right? So it takes some tricky circuit design so they can have replaceable columns, and it takes the ability to laser fuse later. But what that does is increase the yield, because what would be a bad chip that would be discarded, it can be made a good chip by replacing the bad rows and columns with these spare rows and columns. Now there's a limit to how many spares here, so if there's too many faults in here, the chip is not repairable, right? But for a reasonable number of faults, this has been an effective technique. Now, this can be done in DRAMs because there's a highly regular array, regular structure, right? Each row and each column look the same. You could do the same thing with SRAMs. I suppose that's probably been done. Some FPGAs do this because FPGAs also have very regular structure. And in multi-core processors, it's interesting because if you have a multi-core processor where you manufacture it with 16 cores, let's say, and some of those cores are bad, if you designed it right, you can just deactivate those processor cores and then sell the chip as maybe a 12 processor core chip. Right? And I think this has been used for graphics processors, GPUs, and some multi-core processors as well. Right. So that's the sparing idea. So that can help increase yield. Okay, so now so we talked a little bit about runtime bugs. I'm sorry, design bugs. We talked a little bit about manufacturing faults, and we're talking now about runtime faults. So this is the idea that all digital systems occasionally will suffer some kind of fault. Something will go wrong in the chip, and I'll explain how that can happen in a few minutes. But in those cases, in cases where it's critical that there's no runtime errors that happen, we use some fault tolerant design methodologies to tolerate the faults. This is called fault tolerant design methodology. So this gets used in avionics. For instance, the electronics that control the airplanes, the flight, the stabilization of the airplane. You really don't want faults to happen in those processing parts. Right? So you have to find techniques to deal with the faults when they happen. Same thing for spacecraft, particularly electronics that we're sending out into outer space. They're much more susceptible to kind of radiation, cosmic rays, and other other radiation that can cause faults inside the chip. The other one would be medical applications like pacemaker. You want to make sure that doesn't fail, even temporarily, or other medical instrumentation. So we use error detection and correction techniques. And this is commonly used in memory systems because there's so many bits stored, both DRAM and SRAM, it's a likely place that a fault can happen. Right? By the way, error detection and correction it's a common technique that's also used in communication networks because when bits are sent a long distance, there's a chance that those bits will get corrupted, particularly if the bits are sent through the air. So wireless communication is particularly susceptible to noise and other things that can cause faults in communication, not so much in the electronic components, but in the actual transfer of the bits through the air. And so some of the same ideas for error detection and correction that are used in communication networks, we also employ in electronic systems. The other thing that happens is in CMOS devices, as we scale deeply, reliability problems happen due to a variety of physical effects like aging and environmental susceptibility, like I mentioned before, cosmic rays. Lowering the supply voltage actually makes things worse because everything is working at a lower energy level. Okay, so let me just outline what the physical fault mechanisms are that pop up in electronics. There's kind of three classes. There's permanent, transient, and intermittent. So the permanent faults, these are some kind of irreversible physical change. Like I mentioned earlier, some wire on the chip fuses, so it creates an open circuit, right? Because the wires just wear out. Or some transistor oxide breaks down after time, and there's a short between the gate and the drain of a transistor, for instance. Those are permanent faults. And once that happens, the chip is dead, right? And the device will fail. There's also transients, and these are induced by some temporary environmental condition like cosmic rays or some electromagnetic radiation. Let's say the device gets close to some source of electromagnetic radiation, a big magnet or something. And what that could do is induce some current and charge somewhere on the chip, which could flip some bits in a flip-flop, or it could change the output of a logic gate, which would cause a temporary fault. So this is transient. It'll just happen. It'll probably go away once the environmental condition changes. Okay, and then there's intermittent faults. And these will happen kind of occasionally. It creates some instability in the chip. So let's say there's some marginal hardware in the chip, right, where it just kind of works sometimes and works not other times. So the chip heats up and it stops acting correctly because there was some path that was close to being critical path, and that there's not enough timing margin. And all of a sudden, the path might get longer under maybe heat conditions, and then all of a sudden, a path that used to be fine now all of a sudden creates a timing error. Right? So that kind of thing can happen too. So it's that shouldn't happen because the chip should have been tested. When we do the testing before a chip is manufactured, you usually test it at all different kind of worst case scenarios, like if the transistors end up being a little weaker than we thought, or at higher temperatures and other things like that. But still, testing is never perfect, so it could come up in the real world. So intermittent faults often occur repeatedly at the same location, while transients, right, these are environmental conditions that affect the operating of the chip. Big magnetic fields or cosmic rays, they're going to hit the chip in just kind of random locations, right? Intermittent faults also track changes in voltage and temperature, as I said. An intermittent fault could be that the power supply voltage, let's say there's a glitch in the power supply for some reason or another, then that could cause a fault temporarily. But these intermittent faults, they might, if it's marginal design, it might become a permanent fault at some point. Okay, so what I'm not going to go into all the details here, but these are some of the kind of physical effects that create problems in the transistors themselves, right? And these are effects that can get worse with aging over time, and they're also effects that can be voltage and temperature dependent. So what these physical effects, and these are kind of changes within the silicon structure or the behavior of the silicon around the transistors, and the net effect is usually increase the transistor thresholds, right? Which means that transistors will be less strong, there'll be less current for a given voltage, and decrease the mobility. Likewise, it'll make the transistors weaker. Okay, so this could lead to a decreased performance, lower noise margins, and kind of mismatching in the case of, say, SRAM design. Some of these can also cause hard or soft temporary or permanent gate shorts, right, which could lead to degraded transistor performance. Okay, so I'm going to talk a little bit. This is kind of a little fun thing where talk about some transient fault mechanisms in the real world. So where do these transient faults come from that are not kind of due to aging or temperature dependent? These are the faults that come from environmental situations. And for that, I borrowed these slides from this professor in France because he has some nice little stories here. Okay, so we're going to talk about, people call these single event effects. Okay, this is when this is the result of the interaction between radiation and the electronic device. Okay, so a radiation that's all over the place, right? So what these can do, how do they act? They create a free charge in the silicon bulk that in practice behaves like a short life but immense current pulse. So when a cosmic ray or some other environmental interaction with the device happens, there's a temporary release of extra charge within the bulk of the transistor or the silicon, right? So what are the consequences? Well, sometimes bits get flipped, right? If it hits a flip-flop, it might actually flip the state of the flip-flop. Or there's some noise-like signal somewhere on some wire in the chip, right? This kind of just shows what happens if incident particle, kind of hits the surface of the chip, then there's a kind of a track of electron hole pairs, right? If it's ionizing radiation, causes a transient current pulse, right? Now, this will be a problem if it hits near a sensitive place in the chip. Right, so he talks about these are all these single event effects. Right? There's single event upsets, and this would be the change in data of a memory cell. There's multiple bit upsets. There's single event transients, and yeah, other effects. Okay, so the source of these SEEs we've seen it in space missions. This is when people first started seeing these effects back in the early 60s, I guess. And it's quite prevalent out in outer space because there's no atmospheric shield. Here on the surface of the Earth, we're shielded from a lot of this radiation that's floating around in outer space. But out in outer space, we get protons, electrons, heavy ions, cosmic rays, photons from solar flares. So if you're flying a piece of electronic equipment out in outer space, like in a space exploration spacecraft, it's going to be constantly bombarded with this radiation. And it can cause, like I showed on the previous slide, or back here, it can cause this, when it hits the chip, it creates injects some charge into the substrate under the transistors, and this could cause a problem. Right? So here's some kind of famous cases. So alpha particles. In 1978, Intel had to stop a factory because the water was extracted from a nearby river that upstream was too close to an old uranium mine. So the water had trace radiation in it, and that was causing problems with their chips. In 1986, IBM detected a high rate of useless devices after they got manufactured related to the phosphoric acid that they used during the processing, the bottles of which were cleaned with a deionizing gadget, which had trace radiation in it, in those bottles. Here's an interesting one. In 92, the problem came from the use of bat droppings living in a cavern with traces of uranium and thorium. Right? I guess the bat droppings were used to obtain phosphorus, which was used in the processing of ICs, and this led to radiation contaminating the ICs and sitting, in the chemicals, which cause these upsets. Like there's another thing that comes up is that the solder bumps, we talked about the C4 bumps before on the chip. These solder bumps are often made using lead and tin. And if sometimes that lead, those come from minerals where there had been uranium and thorium traces. So there's many cases in history of lead solder being a source of radiation and creating faults on running chips. So I think these days we're much more careful with the purity of the lead and the tin. So cosmic rays have been a headache for space exploration, as I said before. There's famous cases, some listed here, where information was lost on spacecraft data systems because of single event upsets or multiple upsets. Going as recently as 20 years ago. Also, he notes that the GPS satellite network, one of the satellites, is out of commission, probably because of a latch-up problem that happened because of radiation. So this stuff really happens. Cosmic rays at the ground level are less. The highest influence is reached about 15 to 20 kilometers of altitude, and less than 1% of this particle rain reaches the Earth. Most of it is kind of filtered out by the atmosphere. But there's still some that reaches the Earth, and we still see that from time to time. In 1992, there was a case of a system that failed in airplanes because of single event upsets in their SRAMs. A 98 study reported that every day, 1 out of 10,000 SRAMs attached to a pacemaker underwent some bit flips. Wow. So these are real issues that come up. In 2000, Sun, which was a server company that's out of business now, but they had Unix servers, which crashed in dozens of places all over the US because of single event upsets. Cost the company millions of dollars. In 2005, there was a supercomputer cluster. After 102 days, it showed 7,000 errors in its cache memory. Again, probably due to cosmic rays. So I kind of mentioned some of this already. So so the cosmic rays can affect flip-flops, or they can cause kind of glitches on signals in the combinational logic part. So sometimes this can actually lead to faults or temporary faults, right? SRAMs, chips, and SRAM blocks and microprocessors, the microprocessors themselves, FPGAs, ASIC, they're all susceptible. It seems like DRAMs actually are susceptible, but they're less susceptible than SRAMs. So what do you do with it? How do you mitigate these single events or single event effects? One is through technology. So there's certain IC processing technologies that are less susceptible to radiation effects. It's usually called radiation hard processing. This is quite popular with the military and with the space craft manufacturers for obvious reasons. There's things that we can do with the design to make the designs more robust against faults, right? And there's certain things to do in the software. The software can check to see if there's a fault and then maybe retry a computation if it turned out it doesn't check out correctly, right? So there's a whole lot of things we can do there. Let me just show you a couple things. First of all, when we're trying to design fault-tolerant computers or fault-tolerant processing, we need to have a model of the faults in mind, right? So you can think about the physical effects, but you'd like to translate that into something that it's more related to the circuit operation itself. So there's a few low-level fault models that people use for logic circuits. We think about permanent stuck-at faults, right? So stuck-at idea, stuck at 0 or stuck at 1. Here's an example of a stuck at 0. So we have a logic gate here, and let's say there's a fault that happens, and that you could model that in some cases as just one of the inputs is permanently stuck to a 0. Okay, and then you can see what that would do on the rest of the circuit. And sometimes these faults can be modeled as glitches, right? So if we're expecting an input to a logic gate that kind of looks like this, nice transition from a 1 to a 0, it might actually go to 0 and then back to 1 and then back to 0 again. This would be a little glitch that might occur. And then we can check our circuit to see if it can accommodate this correctly. Or another kind of fault might be a slow transition. So where we had a fast transition on one of the inputs, maybe the transition, the fall time is extended out so it doesn't transition as quickly. Or maybe it just takes longer to actually do the transition, right? So again, if we're trying to build a fault-tolerant circuit, we want to make sure that our circuit can accommodate these types of changes without changing its behavior, or where it can still function correctly, right? When it comes to memory blocks or flip-flops or registers, we can model the faults as stuck at 1 or stuck at 0. There could be a failure of the cell to hold a value. There could be when you're reading it, you actually upset the cell. It might slow down the time that it takes to read it, or it might slow down the time that it takes to write a memory cell, right? So again, if we want to build fault-tolerant memory, we'd have to verify that these faults are really the ones that are going to pop up. You look at the physical effects and see if they translate into these kind of models. If they do, then we can design the circuitry so that it can accommodate these conditions. One of the most popular or a popular fault-tolerant design methodology is something called triple modular redundancy. This has been used quite a bit in avionics and in space exploration circuits. Parts of the aircraft or the satellite controller that need to be absolutely perfect and never susceptible to faults can use this technique. It's a very expensive technique, but it can work. So you take what was normally a logic block, this could be as large as a microprocessor, and then triplicate it. So you have 3 versions of it, and then vote on the result. So we put some input in, and it goes to all 3 blocks, right, which are identical copies of this block. And then the results all come out, and then we can vote and take whatever the majority is. So if one of these gets a fault in it, the other 2 presumably are still okay, and those would be the winning result, right? So therefore, we just ignore the bad block. Right? If 2 logic blocks get a, and this idea, by the way, I said it could be as large as a microprocessor. You can do this all the way down to a small level, like down to the level of an adder, for instance. You could do if you had an adder that had to be absolutely fault tolerant, you could put 3 adders there and then vote on the output result. The problem, of course, is if you have faults in both of them, if 2 of them, then you're going to, if they both fail in the same way, you're going to get a faulty result. If they fail in different ways, then the voting circuit will see that there's no majority, there's no 2 that match one another. And so maybe you can raise a flag that says there's a fault, a big fault here, an uncorrectable fault, right? So, like I said, this is most popular in space applications. It's kind of expensive, as you can see, because we have 3 times the cost of, we have to triple the cost of the hardware and then have a voting circuit. And of course, you can ask the question, what happens if there's a fault in the voting circuit? So you have to use some other kind of technique to protect the voting circuit to make sure that it doesn't expose any faults. If there's a fault in here, then it's fault tolerant to that. And there's kind of circuit level tricks that can be used to protect the voting circuits themselves. So the other technique that's used commonly, and this is used in memory systems, but it could be used in logic as well, is error correction codes. So this comes up in memory systems a lot because that's the most likely place that a fault will happen if it's going to happen, right? Because most of the area of our chips is dedicated to memory, and memory is a particularly susceptible place for a fault to show up, because if a cosmic ray or some other kind of radiation hits the chip and it injects a bunch of current into the chip, there's a chance that it could flip a memory cell. So, and if you have a place with lots of memory cells together, then that's a likely place to capture these faults. So, error correction codes have been used commonly with memory systems. It's less frequently that hard errors can occur and cause the chip to permanently fail. Most of these faults that are exposed in memories are called soft errors. It's because they happen, but the chances of them happening again at the same place on the same cell is pretty rare. So it's just a kind of a temporary fault. So, but, you know, if you wrote something into memory, if the processor writes something into memory and then goes and reads it later, it's going to be different. It will have changed. So it would be good to somehow find a way to protect the memory. So where perfect memory is required, like servers quite often these days for warehouse scale computers, and as I mentioned earlier, in spacecraft or military computers, we can use an error correction code in the memory. And so the memories are protected against failures with ECC. Extra bits are added. The way it works, extra bits are added to each data word. The extra bits are used to detect and or to correct faults in the memory system, okay? So in general, what happens is each possible data value is mapped to a unique code word, right? And a fault will then change a valid code word into an invalid code word, which can be detected. So that's the basic idea behind all error correction codes, is we map every valid data word into a unique code word and do it in such a way so if a fault happens, that code word will become invalid and we can detect the fact that a fault happened and possibly correct it. So I'm going to show you in the remaining time then, just about enough time, I'm going to show you how this is typically done these days for memory systems. And it's the principle behind lots of different codes, and it's parity, using parity bits. So here's a simple parity scheme. If we have a data word here, showing it, data word with bits B0 through bit B7. So this is 8-bit data word. We're going to add 1 extra bit to it. So for each data value, before it is written to memory, we tag it with an extra bit to force the stored word to have even parity. So even parity means the number of ones in the word is even. So if it has even parity already, then we make that P bit, the extra parity bit, be a 0. If it has odd parity, we make that P be a 1, and that forces even parity on this code word, in this code word. So the code word is the original data bits plus the parity bit. So this is a simple operation in hardware, as you know, it's just XOR. So we do an XOR reduction. We XOR all the bits together quickly. You could use a tree for that. Get this extra bit, add it to the data word, and then we write this data word to memory. When the word is read from memory, it's checked by computing the parity over the whole code word, including that parity bit. We expect it to be even parity because that's what we forced when we wrote it to memory. But if it comes back as odd parity, we know that an error, a bit flipped somewhere. It flipped from a 0 to being a 1, which would change the parity, or a bit changed from being a 1 to a 0. That would also change the parity. So any one bit flipping here, including the p bit, the parity bit, can be detected by this scheme. So it's effective if the chances of only a single error is high. If the chances of a double error, 2 bits flipping, is if there's a high chance of that, then this is not a good scheme, because this scheme will not check for 2 errors. If 2 bits flip, it'll look like nothing happened as far as from the point of view of this parity bit. It'll remain as even parity. Right. So in fact, in general, what happens is any even number of errors is not detectable, whereas any odd number of errors is detectable. So this scheme is a single parity bit scheme is useful when there's a chance of a single error, but chances of a double error happening in a word is low. Right? So this has been used a lot, and it's a useful scheme, but we can take it further. We can extend this parity bit idea and use more parity bits and get more checking. And when we do that, we have a code called a Hamming code. This was invented by, or I guess invented, yeah, by Hamming. And these are the codes that we use most commonly with memory systems these days. So we use more parity bits to pinpoint the bits in error so they can be corrected. So we can extend this idea of just detecting an detecting error to where we can actually correct the error. So if we have enough parity bits, the value of these parity bits, when we read the value back from memory, the values in the parity bits can tell us which bit was in error, not just if there was an error. So this is called single error correction, SEC. So let me show you an example of how we arrange this for the simple example of 4-bit data. So for a 4-bit data word, we will need to use 3 parity bits. So we're going to combine the 3 parity bits with the 4 data bits, and this will result in a 7-bit code word. These 3 parity bits are going to be sufficient to identify any one of the 7 code word bits. Right? Think about the 3 parity bits as being an address that points to a bit position in the code word where an error happened, where an error occurred. 3 bits will be enough because we have a total of 7 bits. So 2 to the 3 is 8. So 3 bits is enough. So what we're going to do is overlap the assignment of the parity bits over some subset of the bits of the word, over the subset of the data bits and the parity bits to form those parity bit values, and we're going to include those as part of the data word. Okay, so here's how we're going to lay out the data word. Here I'm going to number the bits from left to right, 1 through 7, which is a little different than we normally do, but it's helpful for this Hamming code. We're going to put the bits into the word as shown here with this map. We put parity bit 1 there and bit position 1. That's parity bit 2. And that's the first data bit of the word. And parity bit 3, bit position 4. Bit position 5 is data D sub 2, and then D sub 3, and then D sub 4. So then the procedure is we're going to have parity bit 1. It's going to be the parity over bit position 1, 3, 5, and 7. Parity bit 2 is going to be the parity I'm going to force even parity over 2, 3, 6, and 7. And then parity bit 3 is going to be over 4, 5, 6, and 7. So what you can see, what we did is each parity bit includes, it's going to be the parity of itself, and then 3 out of 4 of the data word bits. Right. And we're going to assign the parity bits so that there's even parity over these sets. Right. Now, the nice thing, the thing that Hamming figured out is if you can assign these groups, as I said. Like, see, P1 protects 1, 3, 5, and 7. That's a group. The assignment of the group comes from looking at the binary coding of the bit positions. So look, P1 we said is going to be 1, 3, 5, and 7. Well, if you look at the binary for 1, it's 0, 0, 1. Binary for 3 is 0, 0, 1. 0, 1, 1, and then 1, 0, 1, and then 1, 1, 1. They all have a 1 in the low bit position. Right, so that's P1. The ones that have a 1 in the second bit position, that's going to be for P2. And the ones that have the 1 in the third bit position, that's for P3. Right, so 4, 5, 6, 7. Okay, so we've made subsets of the data bits and assigned parity bits to them. And we did it in this way by using the bit position. And so this is I'm showing you this because you can extend this to any data width. Right? We're doing 4 bits here to keep it simple, but you can extend it by adding more parity bits. Okay, and then what happens? So that's what our word looks like. So note the parity bits occupy power of 2 bit positions in the word. Parity bits 2 to the 0, 2 to the 1, 2 to the 2. Right? That's the other part of this coding. So on writing to memory, the parity bits are assigned to force even parity over their respective groups, as I said. And then here's the magic. On reading from memory, check bits are generated, right, by finding the parity of the group and its parity bit. Okay. If an error occurred in a group, the corresponding check bit will be a 1. Right? If no error, the check bit would be a 0. All right. So we just take the parity over the parity bit and its associated group. So if it's even parity, that's going to be 0. So that would be no error. If it's a 1, that means there was an error there. Now, these check bits form an indicator of the position of the bit in error. So here's an example. If we compute the check bits C3, C2, C1, it'd be 101. That means 5. That means there was a bit in an error in bit position 5 in D2. And the way this works, really, I mean, if you look at this, C3 says C3 was a 1. That means, because of the way we did the grouping, that the error had to be either in 4, 5, 6, or 7, right? Because those are the bit positions that P3 protects. If C1 is a 1, as it is here, then that says that the arrow is either in 1, 3, 5, or 7. Right? So what's in common here is 7. So when we look at those 2 bits, we know it's either in 7 or it's in 5. But there's no error. C2 says there's no error in 2, 3, 6, or 7. So we can eliminate the ones we had in common before, which was 5. So we can eliminate 5. We can eliminate 6 and 3 and 2, 3 and 6 there. Okay, what that leaves is 5. It's the only one we couldn't eliminate. So therefore, the error had to be in bit position 5. But you don't have to do all this deduction because the value of the C bits tell you a pointer exactly to the bit position where the error happened. So the check bits point to position 5 in this case. Okay, so what we did here is, by our clever positioning and assignment of parity bits, the check bits always address the position of the error. Right. That's a nice thing about Hamming codes. And then if the check bits, when we calculate them after reading from memory, are all zeros, that would indicate no error. All right, so that's the Hamming code scheme I showed you for a 4-bit data word, but it can be extended to larger data words. Just look at the overhead of this. The overhead involved in single error correction.
Excuse me,
John?
Professor.
Yes.
Actually, for the previous example, could we decide that there is no errors in the bit of bit 4 and bit 1?
Bit 4 and bit 1, yes. Well, yes. Oh, how do you eliminate 4 and 1?
Yes, because we can see that both 1, 4, and 5 are probably wrong.
Mm-hmm.
There are both. I mean, 5 is both included in the group 1 and group 3.
But 1 and 4 are not eliminated.
Yeah.
It's because we're assuming there's only one error, right?
Yes. What if there was?
It's only one arrow. It's only one arrow.
That's right.
So it's only possible that 5 is wrong. So both those two groups are wrong.
Yep. Okay.
Thank you, sir.
Okay. So now if we look at the overhead in general, look, we need, if P is the total number of parity bits and D is the number of data bits, then we have P plus D bits in the word. So if P error correction bits are to point to an error bit, then P plus D cases plus indicate no error exists, one case. So we need 2 to the P has to be greater than P plus, or greater than or equal to P plus D plus 1. Right. So what this means is if P is large, P has to be greater than the log of that. So for large D, for large data words, P approaches the log of D. So roughly speaking, the number of parity bits that you need in order to do single error correction is proportional to the log of the data word width. Right. So one thing that's common is, which would catch the case you're talking about before, if we add one extra parity bit, we can cover the entire word. For example, here we can put P4 in here, and what that will help us determine if a double error occurred. So what happens in this case is the C bits will tell us if the C bits were all 0 and P was a 0, there's no error. If the C bits aren't a 0 and P, this extra bit, was a 1, then there's a correctable single error, right? If the C bits are not 0 and P was 0, then there's a double error occurred and we can't correct it. And then if C was 0 and P was 1, then an error occurred in the P4 bit. Right? So that's common. A lot of codes are single error correction, double error detection. So at least if a double error occurred, it can, in the case of a computer system, it can notify the processor and it can notify the OS. And if it wants to, it could redo the calculation or something else. The single error correction will just happen silently in the background. So in modern systems, typical modern code in DRAM systems is to use 64-bit data blocks in memory and 72-bit code words. So a lot of DRAM modules, the DRAM modules that have error correction on them, they will have an extra chip on them that supply another byte of data in the width of the memory. And this will provide single error correction and double error detection using this kind of Hamming code scheme. And the memory controller will have the corrector in it. So I think that's perfect timing, and that was the end of this. Any other questions about this? Okay, good. So that's the end of the content. I'll see you all on Tuesday, and I'll kind of go over topics and talk a little more about the exam. So,
thank you.
Okay, have a good weekend.
Thank you. Actually, today's lecture is quite interesting.
Oh, good. I'm glad you think so.
Yeah, though it's also quite complicated.
Oh, good. Okay, good. I wish I had more time to go into it, but I'll have to do that in another class.
Yeah. See you.
Okay, have a good weekend.
Yeah.
Bye-bye.
Take care.
Thank you. Bye.